Let us start today's class. Today we are going to discuss about the tug of the wars between the different forces in the universe. Like one prominent force in the universe, that is dark matter, another prominent force, that is dark energy. So this tug of war is between the gravity and the repulsion in the universe. And ultimately, which force is going to win, that will decide the fate of the universe. And the next thing that we will discuss about those very smaller particles, millions of times smaller than the electron. And those particles are neutrinos, which are passing through our bodies, and these particles are called the ghost particles. What are their properties and how they influence the universe and why we should know about them. So all of these things we are going to discuss in today's class. So let us start about one thinking, about one idea that was being presented by Mr. Albert Einstein when he was the clerk in the patent office. Yes, Mr. Albert Einstein, when he proposed his theory of general relativity, and before that when he proposed his theory of special relativity, he was the clerk in the patent office. He was not a much celebrated scientist before that, and being a clerk, he is presenting two groundbreaking theory related to the universe, and those theories, literally those theories shocked the world of the physics, established physics at that time. So Mr. Einstein was thinking that what is gravity, वो gravity के बारे में सोच रहे हैं. And before going to the Einsteinian gravity, let us know about the difference between the universe of the Einstein and the universe of the Newton. Yes, the Einsteinian universe and Einsteinian gravity is completely different from the Newtonian universe and Newtonian gravity. For Newton, gravity is a force, and for Newton, universe is flat. There is nothing in the space. Space is vacuum. But for Einstein, gravity is not a force, but it is a curvature of the space-time. And for Einstein, this universe is not flat, but universe is curved. And each and every phenomena is happening in the space, and the space is not empty. Einstein is thinking that whether the space is empty or not. Then Einstein answered that, sir, yes, there was some technical problem. So I was telling you about the universe of the Einstein. So Einstein is thinking that whether empty space is empty, whether what we think that in the space we have the vacuum. So Einstein came with the answer that empty space is not empty, and because of this, what is happening? We are going far away from the Newtonian principles. Newton said that empty space is empty, but for Einstein, empty space is not empty. It is filled with the space-time fabric, and the celestial phenomena is happening on the space-time fabric. And the universe of the Einstein, this fabric of the space-time, it can be curved, it can be stretched, it can be squeezed. It means Einstein's universe is not static as the Newton's universe was. So आइंस्टाइन की यूनिवर्स में क्या हो रहा है? कॉन्ट्रैक्शन एंड इलोंगेशन भी हो रहा है और यूनिवर्स कर्व भी हो रहा है. विद दिस आइडिया, व्हेन आइंस्टाइन proposed the theory of general relativity, so Einstein said something about the gravity, that gravity is the curvature of space-time. And then Einstein, when proposing this theory of relativity, he is saying that every phenomena is happening in the space-time curvature. The more will be the mass, the more will be the space-time curve. Space-time में जितना ज्यादा मास रखोगे उतना ज्यादा space-time curve होता जाएगा. And this distortion or this mass will decide the fate of the space, that how much it should curve, and this curvature of the space-time will decide that how the mass will move. Now let's come to the idea of the dark matter. So this dark matter, Yes, dark matter is responsible for the gravity in the universe. When Einstein is giving his theory, at that time, these things were not so much developed, so much अभी आवाज क्लियर है? अभी भी नहीं क्लियर है आवाज? अभी क्लियर है आवाज? Yes, there was some problem in the voice. So, yes, I was telling you about the Einsteinian universe. वो चीजें मैंने आपको बता दी हैं. Then, what happened? कि now we need to know the composition of the universe, that whether Mr. Einstein was correct or not, whether we have the space-time fabric or not. So we need to know certain answers. To know the certain answers, we went into the Large Hadron Collider, that is in the France and Switzerland border. And Large Hadron Collider is 27 kilometer long tunnel, and it is underground approximately 100 meters. And in the Large Hadron Collider, what we do, we accelerate the proton approximately with the speed of light, and now two protons are coming approximately with the speed of light, and now they are colliding with each other. When they are colliding in such speed, they generate enormous amount of energy, that is approximately 13th tera electron volt, and they disintegrate into the different particles. So why we are doing such things? So that we can have some answer. And even Mr. Stephen Hawking said that the best composition of the universe can be provided. The answer of the best composition of the universe can be provided only by the Large Hadron Collider, and Large Hadron Collider is the biggest experiment of the physics that is going on right now. And many members are participating in the Large Hadron Collider. So, which answers we are searching in the Large Hadron Collider? First is, what is the composition? Composition of the universe. This is the first question that we are searching, that how much matter we have in the universe. For your surprise, let me tell you, whatever you see, whatever star you see, whatever nebula you see, whatever planet and whatever you see, that consists only 5%. So it means we have only 5% ordinary matter, or you can say visible matter. And after this first question, the composition of the universe, rest of the components I will tell you just a little bit after. Then after the composition of the universe, now here we will search why we have the antimatter and matter asymmetry. Antimatter and matter asymmetry. Why each and everything that we know is made up of the matter. When you study the composition of the earth, then you study that this much percent of the nitrogen we have, this much percent of the hydrogen we have, this much percent of the iron we have, hydrogen we have, helium we have. But have you ever heard that this much of the percent in the universe or in the earth we have antimatter? Where all the antimatter gone? What happened to the antimatter? Whether universe took the side of the matter, whether universe was biased, then universe was being expanded. Third question that we are going to answer in the Large Hadron Collider. Initially we know that universe came into the existence because of the Big Bang. Yes, there was Big Bang approximately 13.8 billion years ago. At that time we had the singularity, and in the singularity we have the infinite volume, infinite density, zero volume, and time was zero. Each and everything that we see, that we know, that our telescope see, came from that Big Bang, came from that singularity. And at that time we did not have even a single portion of the mass. So what is the origin of mass? What is the origin of mass? Then right now, before this class, you knew that there are only 3 dimensions of the space. Now I am saying that we are living in the 4-dimensional world, 3 dimensions of the space and 1 unidimension of the place. That is called the space-time fabric, because if you want to move in the space, then you will travel in the time, and if you want to travel in the time, you have to move in the space. That is why we say that this time is unidimensional, and you can go only into the future, not in the past. None of the established physics, none of the theory of the physics suggests that we can go into the past. Yes, even relativity suggests that we can go into the future. So we need to know, in the Large Hadron Collider, we want to answer certain things, that whether we have the extra dimensions. So these are certain questions that will be answered by the Large Hadron Collider. Now let us start with the dark matter. When Einstein said that this universe, in the universe, empty space is not empty, then what it is by which this space is filled? So the answer was that this space is filled by some unseen matter, the matter that we cannot see, and that matter was named as dark matter. It means empty space is not empty, and this empty space is filled by the dark matter. And what is this dark matter? We need to understand something about the dark matter. First and foremost, first property of the dark matter, that it does not interact with the electromagnetic radiation. No interaction. In the electromagnetic waves, this dark matter is not going to interact with the electromagnetic waves. What does it mean by that this dark matter does not interact with the electromagnetic wave? All the spectrum of the light that we know, from the gamma ray to the radio wave, the spectrum of light starts from the gamma ray, then we have X-ray, then we have UV, then we have visible light, then we have infrared, then we have microwave, then we have radio wave, and here the frequency is highest, and here the frequency is lowest. It means this chart is like this: from radio wave to gamma ray, frequency is increasing, and frequency has the inverse relation with the wavelength. So this gamma ray have the lowest frequency, and radio wave have the highest frequency. So in the electromagnetic spectrum, gamma ray will have the highest frequency while the lowest wavelength, and radio wave will have the lowest frequency while the highest wavelength. So this is the inverse relation between the frequency and the wavelength into the electromagnetic radiation, or you can say electromagnetic wave. And this dark matter never interacts with any type of electromagnetic radiation from the gamma ray to the radio wave. This is the first property. And we need to also answer that why it does not interact with the electromagnetic wave, why it does not interact with the electromagnetic radiation. To answer this question, we will have the second property of the dark matter, that dark matter is made up of the massless. Dark matter is made up of chargeless particles. What does it mean by that dark matter is made up of the chargeless particles? It means whatever particle is there by which dark matter is made up of, that particle don't have the charge. Like the atom, or you can say ordinary matter, by which each and everything is made up of, which is the constituent of the ordinary matter. The atom is the constituent of the ordinary matter, and inside the atom we have the neutron and proton in the nucleus, and electron is orbiting in the different energy levels around the nucleus. So this electron is negatively charged, and your proton is positively charged, neutron is neutral, by which proton and neutrons are made up of. Protons and neutrons, they are also made up of proton is made up of 2 up quark and 1 down quark. Up quarks are the positively 2/3 charge, and down quark is minus 1/3 charge. Then we have the Neutron is made up of 2 down quark and 1 up quark. Down quark is minus 1 by 3 charge up, and up quark is plus 2 by 3 charge. So neutrons and protons, they are also made up of charged particles. Here we have the quarks which are charged. Then proton will have the positive charge because it has 2 up quark and 1 down quark. Plus 2 by 3 plus 2 by 3 minus 1 by 3 will be 1. That is why proton will have the positive 1 charge. And neutron is neutral because it is made up of 2 down quark and 1 up quark. Minus 1 by 3 minus 1 by 3 plus 2 by 3 will be 0. That is why neutron is neutral. It means neutrons and protons both are made up of the charged particles. Then we have the electrons, that is also the constituent of the atom. Without electron we cannot have the atom, and electron is negatively charged. And this atom makes the entire ordinary matter. So it means atom is made up of charged particles. It means ordinary matter is made up of the charged particles. But what happens to the dark matter? In the dark matter particles, they are chargeless. And if that there is anything that is chargeless, if the particle is chargeless, then electromagnetic radiation is not going to interact with the dark matter particles because they are chargeless. It will neither interact, nor we will have any reflection, nor they will absorb. So dark matter, it is neither going to interact, nor going to reflect, nor going to absorb the electromagnetic radiation, because electromagnetic radiation क्या है? This is just a photon, and photon interact only with those things which are charged. And if the thing is not charged particle, then photon is not going to interact with those things. And dark matter is made up of the chargeless particle. That is why photon is not going to interact with the chargeless particle. So that is why we will not be able to see the dark matter using the electromagnetic radiation. The third, dark matter. The existence of dark matter is from the birth of the universe, from the Big Bang. So it means if before 13.8 years ago we had the dark matter at the time of the existence of the universe, and today we also have the dark matter, and these dark matter particles and this dark matter is not interacting with anything. So these particles, they must be stable. There is a rule. There is a rule that these particles must be stable. So third, dark matter particle must be stable. Then only it will survive that much of the time. Otherwise, how? This dark matter particle will survive 13.8 billion years. They are surviving from the last 13.8 billion years. Now, these are certain qualities that dark matter is not going to interact with any electromagnetic radiation. It means we cannot see the dark matter using the electromagnetic radiation. First and foremost, this thing. Then dark matter is made up of the chargeless particles. That is why it is not interacting with the electromagnetic radiation. Third, these dark matter particles, they must be stable. That then only they could have survived that much of the time. Otherwise, sorry. Otherwise, they would have decayed into the smaller particles. Fourth, this dark matter particle, they must be heavy. They must be heavy. How much heavy? Some studies says that these dark matter particles must be 80 times heavier. 80 times heavier than the proton. And you know what is the mass of the proton? Mass of the proton is approximately 1 mega electron volt upon c square. This is the mass of the proton. And if it is 80 times heavier than the proton, then it will not be able to remain stable. It would have to decay something else. It would have to decay into some smaller particles. Now, it is approximately 1000, not 1. It is approximately 1000 mega electron volt upon c square, the mass of the proton. And if the dark matter particle is approximately 80 times heavier than the proton, then it is quite heavy for the universe to sustain that much of the heavier particle. This elementary particle must have to decay into the some smaller particles. But if they will decay into something else, then dark matter will not be there. So dark matter is still there. It means they are stable. So these are the 4 properties of the dark matter particles that by which dark matter is composed of. Now अगर हम electromagnetic wave से dark matter को नहीं देख सकते, if we cannot study the dark matter using the electromagnetic wave, using the electromagnetic radiation, we cannot see this dark matter, then how we got to know that we have the dark matter? And you know how much dark matter we have in the universe? Approximately 27%. We have approximately 27% dark matter, and this composition of the universe came from the lambda CDM model. Lambda represents a dark energy, CDM cold dark matter, and lambda CDM model says that in the universe we have approximately 27% of the dark matter and 68% of the dark energy, and 5% is the visible matter. Dark energy, %, and visible or ordinary matter, it is only 5%. Whatever you see, whatever star you see, whatever nebula you see, whatever planet you see, that is composed of only 5%. Rest is the things that we cannot see, the invisible things in the universe, the invisible forces of the universe. 95% of the universe is composed of the invisible things, invisible elements. So now let us talk only about the dark matter. Here, if the dark matter is 27% and visible matter is 5%. Then if we see the composition of the matter in the universe, here I am not talking about the dark energy, if we see only the matter in the universe, then you will see that dark matter is 80% and visible matter, that is ordinary matter, is 20%. It means dark matter dominates the matter of the universe. And as Newton said, that when there will be mass, then we will have the gravity. It means we study the dark matter by the gravity. Yes, dark matter interact with the visible matter with the force of the gravity. So dark matter कैसे interact करता है? With visible matter using gravity. पहली चीज तो dark matter will interact with the gravity. This is how dark matter interact with the visible matter using the force of the gravity, and this is how we got to know that in the universe we have this whopping amount of the dark matter. Then second thing, sometimes dark matter also interact with the weak force. Sometimes dark matter also interact with the weak force, and this weak force is the weakest force in the universe, and this weak force is the fundamental force. There are 4 fundamental forces in the universe by which this universe is being governed. First is your strong force. Strong force is the strongest force in the universe, and its range, the range of the strong force is quite small, within some femtometers, and because of this strong force we have the nucleus, we have the proton, we have the neutron, and after the strong force we have the electromagnetic force, and electromagnetic force work between the charged particles, like nucleus is positively charged and electron is negatively charged, and with the electromagnetic force this atom will be composed of. So for the composition of the atom, electromagnetic force is important. This is the second fundamental force, and range of the electromagnetic force is infinite. Then we have the third force, that is weak force. Weak force is because weak force is responsible for the nuclear fission, and this range of the weak force is quite small, even the smaller than the strong force. Then we have the fourth fundamental force, that is gravity. And gravity, the range of the gravity is infinite. But here the weakest force is what? The weakest force is gravity. If we arrange the forces in the form of their strength, then firstly we will have a strong force, then we will have electromagnetic force, then we will have weak force, then we will have gravity. So strong force is the strongest force in the universe, and gravity is the least, or you can say weakest force in the universe. Yes, we were talking about that strong force interact with gravity and weak force. Mostly strong force, mostly dark matter will interact with the gravity, and because the range of the weak force is so small, तो बहुत smaller range में dark matter will interact with the weak force. So this is how we got to know that in the universe we have the dark matter. Now, what is the historical observation of the dark matter? There was a scientist, Mr. Fritz Zwicky. So Zwicky was observing the dark matter. So Zwicky first, Zwicky was observing a cluster that is known as coma cluster, and in the coma cluster we have more than 1000 galaxies. And yes, clusters are the group of the galaxies. When galaxies meet, they make the cluster. When the clusters meet, they make the super cluster. When the super clusters meet, they make the universe. And the universe that we can see, that is known as the observable universe. The limit by which we can see it is approximately 46 billion light years. So yes, Zwicky was observing a cluster that is named as coma cluster, and in the coma cluster what he observed that the galaxies are moving with so much speed, their orbital speed is so huge. He calculated that in that galaxy that mass is less, and galaxies are moving with so much speed, and if the mass is less, then the gravity is less, and if the galaxies are moving with that much of the speed, then they would have moved away, they would have left that cluster, because gravity is something that holds each and everything together. If Earth is orbiting around the sun, then it is because of the gravity. If moon is orbiting around the Earth, then it is because of the gravity. So Zwicky saw that in the coma cluster we have less mass, we have less gravity, and if we compare that gravity with that orbital force, then that orbital force is quite high. So iska matlab there is something hidden, there is something that we cannot see. So Zwicky came with the concept that there is some hidden matter, there is some unknown matter that is in the coma cluster, with which this coma cluster is filled off, and that for that unknown matter, Zwicky named that Dunkel Materie. Dunkel Materie is a word for dark matter in German. Then Mr. Woods, in his name, we have named the object that comes from the outside of the solar system to the solar system known as Woods cloud. So Mr. Woods, he was observing the Milky Way. So he also came with that idea that in the Milky Way we have a lot of dark matter, because of which each and everything is right now as in the composition. अब इसके बाद क्या होता है? Mr. Peeble, John Peeble, in 2019 he got the Nobel Prize because he established this core concept into the observation that without the dark matter the universe would not have been like that we see right now. So dark matter is compulsory for the structure of the universe that we see right now. And he was observing what? He was observing cosmic microwave background radiation. He was observing CM B. Cosmic microwave background radiation. This is the first light of the universe. And he put this concept of dark matter in this cosmic microwave background radiation. It means how the universe was there when universe was only 3,80,000 years old. It is the story after the Big Bang, just after 3,80,000 years after the Big Bang. So, Mr. Peeble, he was observing the cosmic microwave background radiation, and he came with the idea that without the dark matter, this composition would not have been like that. It means he gave the fundamental for the structure of the universe, and this fundamental was dark matter. Without the dark matter, the universe right now we are seeing, it would not have been like that. And dark matter worked like a glue. It is holding each and everything together. It is holding the entire solar system together. It is holding the entire Milky Way together. It is holding the entire Virgo cluster together. It is holding the entire local group together. Local group is our cluster in which we live. It is holding the entire Linacia supercluster together. Linacia supercluster is what? Linacia supercluster is our supercluster in which local group is, and local group is that cluster in which Milky Way is, and solar system is that solar system, in that star system in which we live, in which Earth is. So the structure of the universe as we see it is only because of the dark matter. Dark matter work like a glue because dark matter interact with the gravity. तो डार्क मैटर एक ग्लू की तरह काम कर रहा है यूनिवर्स को जोड़े रखने के लिए. अब नाउ दीज वर द थ्री ऑब्जर्वेबल evidences of the dark matter before 2019, and for that Mr. Peeble got the Nobel Prize for the physics in 2019. So these are certain things that we studied about the dark matter, that what was the historical significance of the dark matter, who saw the dark matter. Now I was telling you that dark matter is made up of the some chargeless particles. Let us discuss about those chargeless particles. Candidate for the dark matter particle. Candidate for the dark matter particles. Which are the candidate for the dark matter particles? Now let us see about the candidate for the dark matter particles. First is your MACHOs, massive astronomical compact halo objects. Massive astronomical compact halo object. It means these are so massive and compact and halo, and these MACHOs, they are black holes. They are neutron stars. Third, they are the dead stars, or you can say black dwarf. Initially, it was thought that these MACHOs are the dark matter particles, but when we observe the mass of the dark matter, and this was the 27% of the universe, and here their mass is quite irrelevant. So now we have ruled out that these cannot be the dark matter particles. Then second are WIMPs. Weakly interacting massive particles. Weakly interacting massive particles. It means their mass will be quite huge. The WIMPs will have a lot of mass. And dark matter particle के लिए हमारे पास एक requirement 3 that these dark matter particles, they must be chargeless. So WIMPs follow that property. And what are these WIMPs? These WIMPs are like that these are dark matter particles, very, very heavy dark matter particles. And sometimes there would have been dark matter particle and there would have been dark matter antiparticle. And those particle and antiparticle of the dark matter, they must have annihilated each other. When the particle of the dark matter, particle of the dark matter and antiparticle of the dark matter, they will meet, they will annihilate each other. When they will annihilate each other, they will release enormous energy, and that energy will be in the form of gamma ray. That energy will be in the form of gamma ray. And recently we observed this gamma ray in a galaxy. And these WIMPs, their mass is 10 to 1000 giga electron volt. So this satisfies the condition that this can be the dark matter particle. Then after the WIMPs, we have third candidate, Neutrino. And Neutrino is the prediction of the theory of supersymmetry. Theory of supersymmetry says that every particle have a antimatter particle. Every particle have a its constituent particle. And in the standard model, only the matter particle have the antimatter particle. But force carrier like gluon, like photon, like W boson, like Z boson, they don't have the antiparticle, though they don't have the antiparticle. But theory of supersymmetry suggests that these force carrier, they also have some particles. So for the photon, we will have the photino. For Higgs boson, we will have Higgsino. So this photino, this Higgsino, and for your gluon and Z boson, we will have Zeno. And when these photino, Higgsino, and Zeno, they meet, they interact quantum mechanically with each other, they form the neutralino. And neutralino becomes quite heavier, and it is also the potential candidate of the dark matter, and it is also the chargeless. After the neutralino, next dark matter particle, we have a sterile neutrino. This is fourth, sterile neutrino. Why it is sterile? Sterile, the mass of the sterile neutrino, it is approximately 10 kilo electron volt to some tera electron volts. This can be the mass of the sterile neutrino. And yes, 1 minute. It was approximately 900 kilo electron volt. So sterile neutrino, they are from 10 kilo electron volt to some 1000 tera electron volts. So they are quite heavy. And if they are quite heavy, then they can be the potential candidate for the dark matter particle. Now, why this is sterile? This sterile neutrino is also the assumption of the theory of supersymmetry. This also came from theory of supersymmetry. Now, why this is sterile? Because it does not interact with the strong force, it does not interact with the electromagnetic force, it does not even interact with the weak force. This sterile neutrino, it only interact with the gravity. This will only interact with gravity. That is why it is sterile. And this sterile neutrino is being hunted into the ice cube neutrino observatory. We are hunting this sterile neutrino into the ice cube neutrino observatory. So this can be the another dark matter particle. Then we have axion, fifth. This is also predicted by the theory of supersymmetry, and this is a hypothetical particle. Then we have gravitons, 6. Till the date, graviton is the force carrier for the gravity, and the standard model have not explained the graviton, and till the date we have not discovered the graviton. Then 7th is W boson, and as I already told you that dark matter particle, this must be chargeless, but W boson comes into the two flavor, positive and negative, so this is completely ruled out. Then we have 8th, Z boson. Yes, Z boson is chargeless and quite heavy, many times heavier than the proton. So this can be also a dark matter particle. So we have different dark matter particles from the machos. Machos we ruled out because black hole, neutron star, they constitute very small mass in the universe. Then we have the WIMPs, weakly interacting massive particles. And recently we have observed the gamma ray WIMPs. In the WIMPs we will have the dark matter particle, dark matter antiparticle, and occasionally they will meet and they will annihilate each other and they will release the gamma ray. Recently we have observed a gamma ray, and there was another thing that gamma ray can also be the product of the millisecond pulsar. So either it came from the WIMPs or it came from the millisecond pulsar. So we cannot surely say that this was the direct detection of the dark matter. Then after the WIMPs we have the neutralino. Neutralino is made when these photino, these xeno and hexino, they came together quantum mechanically. Then we have the neutralino. Then we have the sterile neutrino, and sterile neutrino interact only with the gravity, it does not interact with the weak force. Then we have the axion. Axion is also a hypothetical particle of the theory of the supersymmetry. Then we have the graviton. Graviton is the force carrier for the gravity. Then we have W boson. W boson, we have ruled out W boson because dark matter particle must be chargeless, and W boson come into the two flavor, W boson plus and W boson minus. Then we have the Z boson. Z boson is neutral, and this can also be the dark matter particle because it is also one of the heaviest particle in the standard model of the particle physics. So these were the some candidate for the dark matter particles. Now, which experiment we are doing to search for the dark matter particle? There are certain experiments that are direct observation of the dark matter. Experiments. First, direct observation. Here dark matter particle will collide and we will have the nuclear recoil. So these experiments are Lux Zoplane. Lux Zoplane is in USA. Then B, we have xenon N1T. This is in Italy. Then we have Panda X. This is in China. These are the direct observation experiment for the dark matter. After the direct, we have space-based observatories, or you can say indirect. Space-based observatories or indirect, it means here the dark matter particle will collide with the antimatter particle and it will annihilate and it will release the gamma ray. So these are your Euclid in L2 point of European Space Agency. Then upcoming Nancy Roman telescope, of NASA, that will also be in the L2 point. Then we have Fermi Gamma Ray telescope, of NASA. So these are, and yes, there is one more damped of China. These are the space-based observatories that right now hunting indirect observation of the dark matter. Then yes, there is one more, but that is not hunting the dark matter particle and dark matter antiparticle. That is your James Webb Space Telescope. James Webb Space Telescope, actually it is studying the gravitational lensing. Or you can say bending of the light. You must be knowing that light is made up of the photons, and photons are massless. And as per the Newtonian gravity, what happens? That to work the gravity, we should have the mass. For the gravity, we must have the mass, and photons are the massless. Still, photons are photons will be influenced by the gravity. Here we will have the influence of the gravity of the photon, but for that we should have a lot of enormous amount of the gravity, and that gravity comes because of the dark matter, because we have humongous amount of the dark matter in the universe, and because of the dark matter we will see the bending of the light, we will be seeing the gravitational lensing, and because of the gravitational lensing we will be able to see behind the galaxies what is behind the galaxy. And yes, James Webb Space Telescope have observed this gravitational lensing, and this is not only the first evidence of the gravitational lensing, and gravitational lensing was the direct prediction of the Einstein's general relativity. Even in 1919, Mr. Eddington proved the gravitational lensing when he saw at the time of solar eclipse light tilted. So this is the observation of the James Webb Space Telescope for the dark matter. Then we have some collider experiment. Third, first was direct, second was indirect and space based, third is collider, and this is your Large Hadron Collider. Here we are researching for the dark matter. Then fourth, with the neutrino slab, we are experimenting the dark matter, we are hunting for the dark matter. Here we have the ice cube neutrino observatory. So these are certain experiments that we are doing to hunt the dark matter. अब now what is the significance of the dark matter? अभी आवाज प्रॉपर्ली आ रही है ना? अभी आवाज प्रॉपर्ली आ रही है? ठीक है, चलो आगे करते हैं. सिग्निफिकेंस. First significance, we will be able to predict the best cosmic structure, the structure of the cosmos. We will be able to predict the cosmic structure. Second, we will be able to make the atlas of the universe. Third, and the next, they will be the spillover effects, because to make the dark matter laboratories, we are making some ultra sensitive detectors, and if we will have the ultra sensitive detectors, and we are having some very huge along with the detectors, we have some very huge magnetic components. So with those, we will have some spillover technologies, like we will be able to use this technology in the quantum computer. In the medicine, in the security. So these will be the some significance of the dark matter. So this is how we have completed the dark matter. Now next, we will be studying about the dark energy. Next topic will be dark energy. What is the composition of dark energy in the universe? It is approximately 68%. We have 68% dark energy in the universe, and dark matter was responsible for what? It was responsible for holding the universe together, and it was interacting with the visible matter, with the gravity. So yes, dark matter was 27% and dark energy is approximately 68% of the universe. Now, when Einstein was giving his theory of relativity, so Einstein took the consideration of the gravity, because at that time we knew that there is gravity. No one knew about the dark energy, that what this thing is. So, and everyone knew about the gravity. So Einstein was writing his theory of relativity. So when he was writing the theory of relativity, he wrote about the gravity. He gave the equation, relativistic field equation, and over there he put the gravity. But someone asked, sir, if there will be only gravity, if there will be no force to balance the gravity, then what will happen? This universe will start contracting, and ultimately what will happen? Each and everything will be collapsed into a single point with the force of the gravity. तो आइंस्टाइन को लगा यार दिस थिंग इज करेक्ट, ये तो सही बात बोल रहा है. तो टू बैलेंस द फोर्स ऑफ द ग्रेविटी he put lambda into his relativistic equation. Now when he put lambda, and this was the cosmological constant, but after some time Mr. Edwin Hubble, he saw that universe is expanding. It means universe is not stable, it is expanding. So Einstein said that this was the gravest error that I have done in my general relativity, and Einstein took it back. Einstein ने अपनी relativistic equation से lambda को हटा दिया. उन्होंने बोला when universe is expanding, this lambda, how the universe can be constant. After some time, what happened in 1990s? In 1990s, we came to know, initially it was the prediction that when expansion started with the Big Bang, and there will be a time when this expansion will be slowed down because of the gravity. But this did not happen. In 1990s, we got to know that this expansion of the universe, it is accelerating. ये तो तेज हो रहा है पहले से. It means there is some force because of which this acceleration is increasing. अब this expansion is increasing, expansion is accelerating. Now again his lambda came to relief. Now again lambda re-emerged in his theory of relativity, and yes, we got to know that his theory was complete. His theory was, he did the most accurate prediction of lambda, and this lambda today this lambda is known as dark energy, and this dark energy is responsible for the accelerated expansion of the universe. So this was the starting point. So yes, we took consideration of the dark energy, and it is the 68% of the universe. Now why this is the thing that when universe is expanding, this dark energy is not diluting. इसको हम कुछ images के थ्रू समझने की कोशिश करते हैं. As per the Einstein, he said that this lambda is the intrinsic property of the space time. ये जो lambda है, this is the intrinsic property of the space time. This dark energy is the energy of the vacuum. और उन्होंने बताया कि that its density is uniform in entire universe. हर जगह इसकी डेंसिटी एक जैसी है, कहीं भी इसकी डेंसिटी कम या ज्यादा नहीं है. This thing also told by him. Then फिर उनसे पूछा गया कि सर ये एक्सपैंड क्यों कर रही है. तो एक्सपेंशन के लिए उन्होंने बताया कि दैट वी हैव द प्रेशर, एंड प्रेशर इज प्रोपोर्शनल टू ग्रेविटी. The more the pressure, the more will be the gravity, and each and everything will start collapsing because of the pressure and because of the gravity. फिर उन्होंने बताया कि that this dark energy, that is lambda, it is equivalent to negative of the pressure. It is equivalent to negative of the pressure. It means now this will work, this negative pressure, it will work like anti-gravity. Now this negative pressure, it will start like working anti-gravity, and when it will start working like anti-gravity, देखो प्रेशर में सब कुछ नीचे जाएगा, सब कुछ कंप्रेस होगा, बट नेगेटिव प्रेशर सब कुछ एक्सपैंड करेगा. तो यही तो है ना एंटी-ग्रेविटी, यही तो है ना डार्क एनर्जी एक्सपैंडिंग द यूनिवर्स. एंड द सेम थिंग इन दिस सेम इक्वेशन वी गॉट टू नो कि दैट सर दिस lambda, it produces the negative pressure, and because of the negative pressure we have the negative gravity, or you can say anti-gravity, because of which we will have the acceleration in the expansion of the universe. Now next thing is that what is the density of the dark energy. I told you that universe is expanding with much speed, and this speed of the expansion of the universe is accelerating. And when this speed, अब देखो नया स्पेस बनता जा रहा है. In the vacuum we are getting new space. So whether in the new space the density of the dark energy decreases or remains same, or whether the quantity of the dark energy increases or remains the same. These are the some fundamental questions. So now let us compare with the matter, radiation and dark energy. As we have finite amount of the matter, so when the expansion will be there, it means volume increased, and when the volume will increase and you have to put the same amount of the matter on that volume, so density will decrease ना. Ultimately जब हम अभी है and it expanded more और matter उतना ही था, उतना ही matter रखता, तो density decreased. So if the matter's density will decrease, it means the gravity between the matter will decrease. Density ज्यादा होगी तो gravity ज्यादा होगी, density कम होगी तो gravity कम होगी. And this expansion of the universe, even it have very adverse impact in the radiation. यहाँ पे तो कम impact हुआ, यहाँ पे और ज्यादा impact हुआ, because photons will be stretched as the universe will expand. The radiation, or you can say photon will be stretched, and the more it will be stretched, it will go towards the redshift. It means here even the density will more decreased than the matter. Now come to the dark energy, and dark energy is explained as the energy of the vacuum. And dark energy, as per the Einstein, dark energy always remain constant, because dark energy, that lambda was the universal constant. So if lambda is the universal constant, so its density should always remain same. Even in the expanding universe, जब यूनिवर्स इतना बड़ा था तब भी उसकी डेंसिटी सेम थी. यूनिवर्स फिर बड़ा हुआ, मिडिल यूनिवर्स, तब भी डेंसिटी इतनी ही है, और जब यूनिवर्स आज के टाइम पे इन टूडेज एज द डेंसिटी इज सेम, इट मींस द अमाउंट ऑफ द डार्क एनर्जी इंक्रीज्ड. अब तुम ये सोचो कि इफ द अमाउंट ऑफ द डार्क एनर्जी इंक्रीज्ड, so and density is same, so tomorrow जैसे right now what is the composition of the universe? Dark matter is 27%, dark energy is 68%, and visible matter is approximately 5%. This is the composition of the universe. When amount of the dark energy is increasing, tomorrow what will happen? Tomorrow or after trillions of years, what will happen? This dark energy will become 99.999%, and rest will be the dark matter and visible matter. So it means here in today's case dark energy is winning, because it will always its density will always remain constant, because of which in the expanding universe dark energy is increasing. So आ कहां से रही है dark energy? From where this dark energy is coming? Now you will say कि sir, if new energy is created, are you referring to that new energy is being created? Yes, I am saying that this new energy is being created in the universe. फिर तुम बोलोगे sir, isn't it the violation of the Einstein's law that energy is neither being created nor being destroyed? Now think about it, whether I am correct or not. I am saying that energy is being created in the universe. New energy is being created in the universe. And I am asking if this new energy is being created in the universe, then whether this is the violation of the Einsteinian law that energy cannot be created, energy can neither be created nor be destroyed, the energy is constant. Can someone give me the answer of this question? Whether I am wrong or Einstein was wrong? And I am teaching you the things which were said by Einstein. Both the things are said by Einstein. That when the expansion of the universe will be there, then what will happen? Then new energy will be created. और आइंस्टाइन ने बोला कि there is the conservation law of the energy, that energy can neither be destroyed nor be created. So कोई आंसर देना चाहेगा इस बात का? मैं बोल रहा हूं कि जैसे जैसे यूनिवर्स एक्सपेंड हो रहा है वैसे वैसे नई एनर्जी बन रही है, और आइंस्टाइन बोल रहे थे कि एनर्जी इज कांस्टेंट, इट कैन नाइदर बी क्रिएटेड नॉर बी डिस्ट्रॉयड. कोई और आंसर देना चाहेगा? Can someone else try the answer? हाँ, तुम्हें तुम्हारे साइंस टेक्नोलॉजी वाले सर ने बताया होगा कि दैट एनर्जी रिमेन कांस्टेंट बिकॉज इट इज सेड बाय आइंस्टाइन. देखो बिल्कुल सही बात है, इट इज सेड बाय आइंस्टाइन कि एनर्जी रिमेन्स कांस्टेंट, इट कैन नाइदर बी क्रिएटेड नॉर बी डिस्ट्रॉयड. तुम्हारे टेक्नोलॉजी वाले सर ने बिल्कुल सही बताया होगा. हाँ, तो बात सुनो, एनर्जी कैन बी क्रिएटेड एंड एनर्जी इज बीइंग क्रिएटेड, द न्यू एनर्जी इज बीइंग created. The thing that I am saying, when Einstein is saying that energy is constant, it can neither be created nor be destroyed, it applies only into the locality. It applies into the local scenarios, not into the cosmic scenarios, not into the global scenarios. When space is itself not stationary, when it is dynamic, when space is expanding, then what is energy? Energy will also be created, na? We have seen in the field relativistic theory of the Einstein that the density of the dark energy will remain same, and dark energy is a component of the energy of the universe. 68% of the universe right now is filled with the dark energy. And when the new space-time fabric is being created into the vacuum, it means dark energy, the same density have to fill that space-time fabric. It means new energy is being created. It means amount of the dark energy is increasing. Ultimately energy is being created by the universe. Energy ban rahi hai, and that thing, that energy always remain constant. It can neither be created nor be destroyed. It applies locally. It applies into the local universe, into a smaller universe. But when the universe is expanding with more than the speed of light right now even, so it does not apply over there. It does not apply into the new space-time fabric which is being created right now somewhere in the universe, far beyond in the edges of the universe. Over there, this law does not apply, the conservation of the energy. Don't befool yourself. And as there will be more dark energy, अब देखो यहां पे कैसा साइकिल लूप बन रहा है. Dark energy is causing the expansion, and because of the expansion we have the more dark energy, and when we will have the more dark energy, then there will be more expansion. This is a loop. Dark energy is causing the expansion, and when there will be expansion, we will have the more dark energy. When we will have the more dark energy, we will have the more expansion. So ultimately expansion is winning. Now, ये तो हमने डार्क एनर्जी की बात कर ली कि दैट व्हाट इज हैपनिंग इनटू द डार्क एनर्जी, एंड नाउ व्हिच आर द experiments that are being done to map the dark energy. One of them is Euclid, that I told you previously that Euclid is searching for the dark matter and dark energy. अब Euclid क्या कर रहा है? It is searching the dark energy and dark matter using the weak gravitational lensing. What is the impact of the dark energy? What is the impact of the dark matter? Then the upcoming telescope, that will be the Nancy Roman telescope, that will also map the dark energy into the universe. Then yes, DESI experiment, it is also related to the dark energy. So these are certain experiments that are being done for the dark energy. Now next is your, अब डार्क एनर्जी में अभी डेसी ने एक बात बताई कि when we mapped cosmic microwave background radiation, at that time we saw that this expansion of the universe was not that much, and when right now we are seeing using the James Webb Space Telescope, the expansion is quite huge. उस टाइम पे हमने देखा कि डार्क एनर्जी वाज लेस, हियर हमने देखा कि डार्क एनर्जी वाज क्वाइट हाई. This is called the Hubble tension. When anything that is more than 5 sigma, when two results does not match, that is called the sigma discrepancy. And here we have the Hubble tension. Here the discrepancy is more than 5 sigma. This is the discrepancy, and when this much of the discrepancy is that, it means we have to revise the things, or there can be another thing, we have got the new physics. Either the results should be same, and this is called the Hubble discrepancy, or you can say Hubble tension. When in two results we have such discrepancy. अब यहाँ पे वहां पे हमने देखा cosmic microwave background radiation in the late universe, and in the early universe we are seeing the Cepheids, we are seeing the supernova, we are seeing the pulsars, millisecond pulsars. So they are behaving differently. So it means that there is some thing that we don't know about the universe. There is a lack of knowledge in our understanding of the universe. So these telescope, JWST, Hubble, they will try to solve these problems, that which were the discrepancies. Now what will be the end of the universe? How, in the end, how we will see that this universe is? So to see the end of the universe, there are three concepts that have been proposed. one experiment says that this dark energy, amount of the dark energy, or you can say density of the dark energy, it does not always remain constant. It changes. With time it changes. वैसे होना चाहिए, dark energy should always be how much? -1. This should be there. This should be for the purpose of the constant dark energy. But when this -1 changes, then different thing happens. If this decreases, then the expansion decreases. If this increases, then expansion increases. अब यहां पे क्या हो रहा है? There will be 3 concepts. 2 for the dark energy, 1 for the dark matter. Whosoever will win, that will be the fate of the universe. If dark matter, or you can say gravity wins. If gravity wins, then what will happen? Each and everything will started collapsing because of the force of the gravity. And the universe will die a very hot death. Because at the time of the Big Bang, the temperature was in the billions, trillions of degrees Celsius. At the time, temperature was 10 to the power 32 Kelvin. That temperature you cannot imagine. And that is quite hot. We cannot generate that much of the temperature in the earth. Even in the core of the stars, the temperature is only in the millions of degrees Celsius. In the core of the sun, the temperature is 15 million degrees Celsius only. And at the time of the Big Bang, the temperature was 10 to the power 32 Kelvin. बिलियन में कितने? 9 जीरो आए ना. मिलियन में कितने? 6-7 जीरो आए. 6 जीरो आए. In the core of the sun, the temperature is in millions of degrees, 15 million degrees Celsius. And I am talking about 10 to the power 32 Kelvin. अब वहां पे केल्विन बोलूं या सेल्सियस बोलूं, it doesn't matter, because the difference will be only of number 273. अब जब 10 to the power 32 की बात करो तो 273 is negligible. So if the gravity will win, if the dark matter will win, then what will happen? Then the universe will die a very hot death, and this is called the big crunch. This is called the big crunch. Each and everything will again come into the singularity. Depending on this lambda, if this lambda changes, this big crunch can happen and another fate can happen. If this lambda changes, then another thing is big freeze. Right now universe is expanding. अब stars will go away from the planets and these galaxies will go away from clusters. सब कुछ दूर दूर जाता जाएगा, because universe is expanding, and on that universe we have the stars, we have the galaxy. So each and everything will go away. Then after some time, we will be, one star will not be able to see another star. That will be the distance. Then between the planets and star, that will be the distance, that the light of the star will not be able to reach to the planet. And after some time, what will happen? The fusion in the stars will also stop in the core. Then star will start getting cold. और मैटर को काम करने के लिए कुछ बचा ही नहीं कि नया स्टार बन पाए, because each and everything is so apart. So what will happen? There will be a very cold death of the universe. That is called the big freeze. That is called big freeze. There can be another thing. There can be another thing. If this lambda increases, then what will happen? Then अभी स्टार को हम दूर ले गए, प्लैनेट्स को हम दूर ले गए. Even there will be a time, because of this dark energy, it will rip apart the atoms also. Atoms will be ripped apart. When atoms will be ripped apart, it means this will be your big rip. Each and everything that we know will be ripped apart because of the dark energy. So this will be the end of the universe. This is how universe can die, either by the hot death, or by the cold death, or by the ripped death. अब चलो उस 5% के बारे में बात कर लेते हैं, जो बचा हुआ 5% है. That is visible matter. Visible matter. In this visible matter, now we are talking about only 5%. 68 was what? Dark energy. Then 27 was what? Dark matter. And this 5% is visible matter. Now on this 5%, in the nebula, we have free hydrogen and oxygen. Sorry, we have free hydrogen and helium. This is beta 4%. Now you are left with only 1%. And when you are left with only 1%, here 0.5% is with the stars, all the stars that you see. Stars का केवल 0.5% है of the universe. So this is how smaller we are. 4% is with the nebula. और उसमें मोस्टली हाइड्रोजन हीलियम है. मतलब कि यूनिवर्स में इन द विजिबल मैटर विच इज द एलिमेंट दैट डोमिनेट, it is hydrogen and helium. In the stars, what is fusing? In the stars, hydrogen is fusing into the helium. Then beta 0.3%, we have neutrino. Then 0.03%, we have heavier elements. Heavier elements by which all the planets are made up of. These are the heavier elements. Heavier elements by which all the animals, all the insects, all the organisms are made up of. Uranium, plutonium, gold, जो तो बहुत प्यारा है. What is it is? ये तो केवल 0.03% है सर. स्टार के पास केवल 0.05% है. This much big is universe. Now there are certain other terms that we need to know. One is Hubble limit. Hubble limit, or you can say Hubble circle, or you can say Hubble boundary. This is the first term. Then second term is cosmological event horizon. Then third term is observable universe. What do you know about these terms? क्या होते हैं? And one more we can add, future limit. These terms are very important for the purpose of the prelims. Prelims के लिए ये term बहुत ज़्यादा important है. क्या है? Hubble limit, Hubble circle, and this your Hubble boundary. What it can be? कोई उत्तर देना चाहेगा कि आप सब शांत ही बैठे रहेंगे? उत्तर देना भी कई बार अच्छा होता है, हमेशा शांत बैठे रहना अच्छा नहीं होता है ना. हिंदी समझ आए तो हिंदी में सुन लो, अंग्रेजी समझ आए तो प्लीज ट्राई टू गिव द आंसर्स, है ना. डोंट बी सो शाई, बिकॉज इन द इंटरव्यू, इन द मेंस यू हैव टू राइट, इन द इंटरव्यू यू हैव टू स्पीक इन फ्रंट ऑफ द इंटरव्यूअर. So we need to always be prepared. We need to always be prepared to give the answers. In the interview you can't say ना सर मैं तो नहीं बोलूंगा, मेरा तो मन नहीं बोलने का. In the means you can't say मेरा तो मन नहीं लिखने का, हाथ दुख रहे हैं. It will not be happen ना. हाँ तो कैन यू आंसर? किसी भी एक के बारे में पता हो, किसी भी एक के बारे में पता हो तो प्लीज ट्राई टू आंसर.